8.4 is confidence intervals for population proportion. So I've got a little quote here. The probability of success is difficult to estimate, but if we never search, then the chance of success is 0. This is a famous physicist. We worked with proportions before. This is where we're looking at the probability of success and the probability of failure. So with the probability of success, what we're going to do is we are going to take the number of successes divided by the number of trials, and that's going to give us our sample proportion. Sometimes you'll see it as p hat. This section seems to use p with the apostrophe there, but it's the same idea. Just like in 8.1, for a confidence interval, we're going to take the sample proportion, or the estimated proportion of success. We're going to subtract the margin of error, and we're going to add the margin of error to find the confidence interval. Again, we're looking for confidence, and we want the true population proportion to be between the two limits of the confidence interval. Now, we do have a formula for margin of error, but we can also let GeoGebra do that for us. So we're probably not going to mess with this, but just remember that we are going to use the p plus q is equal to 1. So if we have p, but we need q, then we would find q by taking 1 minus p, just like we've done in the past. We're going to use z-scores. We're not going to use t-scores. We only use t-scores if we're finding the confidence interval with the sample mean, and we only have the sample standard deviation. Now, I didn't see any problems in Knewton, but in order to use these formulas, we need to have that our sample size, n, times the estimated proportion of success would have to be greater than 5, and the same thing with the failure. So our sample size times q would have to be greater than 5. Here's our formula for standard error. Now, sometimes it's going to say standard error. Sometimes you're going to have a sigma with the little p apostrophe underneath. Those mean the same thing. So different problems are going to show it to you different ways, and I'm going to show you both of those. With standard error, we can let GeoGebra do it. With GeoGebra, though, it usually wants a confidence level. Well, you can put any confidence level in. I like to put 99 because I like to be 99% confident. But you can put any confidence level in, and then at that point, you put in the number of successes and the sample size, and GeoGebra is going to give you the standard error. But I'm going to show you how to do both. I'm going to show you how to do the formula and then show you how to do GeoGebra. Now, for the minimum sample size, we have to use our calculator. GeoGebra does not do this one for us. So you're going to have to use your Casio or whatever calculator you're using to get the minimum sample size. And we'll go over that together. One important thing is that if they do not give you P and Q, if they don't give you the estimated proportion when they ask you to find the minimum sample size, you're going to actually just let P equal 0.5 and Q equals 0.5. It's a good start point. So we're going to go to the same area in GeoGebra as we have for all of Chapter 8. We're going to go to probability. Well, we're going to go to classic first and then probability. Then we're going to click on the statistics tab. At that point, we want the z estimate of a proportion. We're still going to use z, and we're looking at proportions. We only need 3 items. We're going to have the confidence level, the number of successes, and the sample size, and then GeoGebra is going to do all the work. An entertainment company surveyed 360 elementary school children. So that's our sample size, and found that 153 of them were above grade level readers. Find the standard error for the sample proportion of elementary school children who were above grade level readers. So we're going to do it both ways. We're going to do it in the calculator, and then on the next page, I'll show you how to do it in GeoGebra. So the standard error, the formula is the square root of P times Q divided by N, our sample size. In this case, we can find P. What we're going to do is we're going to take the 153, our number of successes, over 360, which is our sample size. When we do that, we get 0.425. So that's our estimated proportion of success. Now we also need Q, but Q is just 1 minus P. So what we can do is just put that into the calculator, right? You can see here, I put, well, first I hit my square root key, then I put the 0.425, multiplied that times 1 minus 0.425. Instead of finding Q, I just let the calculator do the work, and then divided by 360. When I did all that, I get, they went 3 decimal places. I get 0.026. So that is our standard error for this data. Now on the next page, I want to show you how to do this in GeoGebra. The only 2 things we need are the number of successes, 153, and the sample size, 360. Okay, so you're going to go into GeoGebra, hit GeoGebra Classic, then you're going to go to probability. Now, when you hit probability, you get the normal curve, but we don't want the normal curve. So we're going to click Statistics, the Statistics tab. When you do that, you have a drop-down window right here. You have to change it to Z estimate of a proportion. When you first go in, you're going to see something about a null hypothesis. Well, we don't want that for chapter 8. So we're going to change it to Z estimate of a proportion. We're going to put in the 153 and the 360. Now, it does not matter which confidence level you put in because we're only looking for standard error. So I put 99, but it doesn't matter. You'll see that the standard error will not change. You can put 95 in there, you can put 90, you can put 80, it doesn't matter. The standard error, which is sitting right here, will stay the same. And remember, it could look like this. It could be the word standard error, or in GeoGebra, it's SE. And you can see if I round that to 3 decimal places, I also get the 0.026 like we did on the page before. So up to you, whichever one works best for you. All right, let's try another one. I'm gonna go ahead and do the formula, but you could pop that into GeoGebra. So it says, in a recent survey of 100 new vegetarians, so that's my sample size, that's my denominator, 74 said that their new plant-based diets were helping them feel healthier. And then it says, find the standard error for the sample proportion of vegetarians who feel healthier. All right, so we're looking for the standard error. So I grabbed my formula here. I need to find p hat though. So that's going to be 74 over 100, which gives me 0.74. And now, and I know Q is 1 minus P. So I'm going to use that knowledge to put it into the calculator all at the same time. So I hit my square root key. I put in the 0.74. And then I multiply that times 1 minus 0.74. Now, I didn't say in the last problem, but it's critical that you have parentheses around the 1 minus 0.74. Because of order of operations, we want to make sure we subtract before we multiply. And then we put it over the sample size, which is 100. And there's our standard error. They want 3 decimal places. So we get 0.0, no, we don't. Oh, yep, we do. So 0.04, and then the 3 gets rounded up to a 4. Yep, I'm good. I don't know what I was looking at. All right. In a recent survey of 300 students at a university, so that's my sample size, 300, 120 stated that they had at least one cold during the past academic year. So unfortunately for us, the success is having at least one cold. So X is going to be 120, or the number of successes. They want us to find the point estimate. So that's p hat. So that's going to be 120 divided by 300, and that gives me 0.4. So I'm going to put 0.4 right here. Then they ask me, they give me the sigma with the P and the dash like that. That's the standard error. So I know how to do that. I either put it all in GeoGebra and just make up a confidence level, or I can do it in the calculator. So I hit the square root, then hit the fraction key. I'm going to put 0.4 for P, and then I'm going to put 1 minus 0.4, because that gives me Q, right? Q is 1 minus P hat. And then that's all divided by 300, the sample size. So once I've done all that, I want 3 decimal places again. So I get 0.028. Suppose a clothing store wants to determine the current percentage of customers who are over the age of 40. How many customers should the company survey in order to be 90% confident? All right, so 90% is our confidence level. So we want to be 90% confident that the estimated sample proportion is within 4 percentage points. So remember that word within tells us that that's our margin of error, but we have to be careful with these. It gives us to us as a percent, but we can't put a percent into the formula. So we need to go ahead and change that to a decimal. And of course, drop the percent sign when we do that. Okay, now it doesn't literally say what is the minimum sample size, not like it did in 8.2, but it says how many customers should the company survey. So that is telling me that this is the minimum sample size. Okay, so I'm going to go and grab my formula for minimum sample size. And we can see we're going to need Z, we're going to need P, need Q, and we need E. Well, we have E. Let's go ahead and find Z. So the problem with the Z table is we need to know alpha divided by 2, because remember this is, confidence interval is a 2-tail. So in the middle, I have 90%, but I'm worried about the 2 tails. So so alpha is equal to 1 minus 0.90, which gives me 0.10. So I've got 10%, right? Because I have 90% in the middle. That means I'm left with 10% because it has to equal 100%. But I have the 2 tails, so I have to split up the 10% into the 2 tails. So I need alpha over 2, which would be 0.10 divided by 2. And that gives me 0.05. So I'm going to come over here, and that is the Z value that I'm going to grab. I need the Z for 0.05, which is actually 5%. Okay, so that's my Z value. Now, they didn't give me P or Q, or they didn't give me any information. They didn't give me sample size. They didn't give me number of successes. And so when they don't give you any of that, you're going to make the assumption that P and Q are both 50%. So we've got 50-50 here. And then on the bottom, we're going to go ahead and put our E. Now you could put 4, if you have a Casio, you could put 4% and then put that squared, but it's probably better to go ahead. I messed up in class today. I put 4 squared down here and oh my goodness, I got a crazy answer. I got an answer that I only needed to talk to one person, which didn't make any sense. How can I only talk to one person and know anything about the clothing store? And then I realized I didn't change it to a decimal. Okay, so if you put all that in the calculator, go ahead and hit your fraction key, put the 1.645 squared. Now the 0.5 times 0.5, those are not squared. And then go into the denominator and put the 0.04 squared. When you do all that, you get 422.8164063. It goes on and on. So that tells me that I need to talk to 423 people in order to be 90% confident and to be within 4 percentage points of the true population. All right, let's try another one of these. So suppose a company wants to determine the percentage of customers who shop online. How many customers should the company survey in order to be 92% confident that the estimated sample proportion is within 3 percentage points of the true population proportion? So this is my E, but this is percent. So I need to change it to a decimal. All right, so what it asked me is, how many customers should the company survey? So that's telling me what is the minimum sample size, even though it doesn't use those words. That's what it's telling me. All right, so let's go over here and deal with our alpha. So alpha is going to be 1 minus 0.92. Right, because we're going to take 100% minus 92%. That gives me 8%. But that's 2 tails, and I need to cut that in half. That's a weird one. We haven't seen one that looked like that. So we're actually going to have 4% in each tail. And that tells me I want to use 1.751. That is squared. The Z is squared. They didn't give me any information about successes. So I'm going to make the assumption that it's 50-50. Now, all the problems I saw in Knewton are that way, that it's going to be 50-50. And then finally, on the bottom, we're going to have 0.03 squared. And once we do all that, look how many people we have to talk to. We have to talk to 851.6669. So we're going to round up. But remember, we always round up. These examples didn't really tell us, but we always round up on sample size. So even if this had been 851.116, we would still round up to 852 because we want to be on the safe side. If we want to know that we're 92% confident and that we're within 3 percentage points of the true population proportion, we have to be on the safe side and go up to the 852. Now, this number got a lot bigger. The reason it got bigger is that, for one thing, we're more confident, and also we are closer in percentage points to the true population. So all of those make a difference of whether you need to talk to more people or whether you can talk to less people. This problem threw me off when I first saw it. A research intern would like to estimate with 90% confidence. So CL is equal to 90%. the true proportion of employees who hold two jobs. No preliminary estimate is available. The researcher wants to estimate, or excuse me, wants the estimate to be within 3%. So that tells me that E is 3%, which is also 0.03. So let's see. They showed us the calculation, but they did something wrong, and they did that on purpose. So let's find alpha. We're going to take 1 more minus 0.90. Okay, so that tells me I want 1.645. So that works. That was here. We don't know P and Q, so we're going to use 0.5 and 0.5. Ah, look what they did on the bottom. They did the same thing I did. And so it looks like you're going to only talk to one person? That's crazy. That doesn't work. So what's wrong is the 3. It should actually be 0.03 squared in the denominator, not just the 3. I also saw one of these in the homework where they found the wrong z-score. So check for that too. In case the denominator's good, check and see if they get the wrong z-score. Now, if they just ask for the confidence interval, just let GeoGebra do the work. Don't do extra work. So Emma wants to estimate the percentage of people who use public transportation in a city. So that's her success, is using public transportation. She surveys 140 individuals and finds that 62, so that's my success, use public transportation. Find the confidence interval for the population proportion with a 99% confidence level. Okay, so we're going to go to GeoGebra. We're going to go to GeoGebra Classic. We're going to hit probability, but when you first hit probability, you get the normal curve. So you're going to click the tab that says statistics, and then you're going to change that first drop-down window. You're going to change it to Z estimate of a proportion, because we know we're in a proportion. Going to put in the 99% confidence level, 62 successes, 140 for the sample size. And like magic, GeoGebra is going to give you the answer. So we want a confidence interval, so we're going to come down here to the lower limit and the upper limit. So our lower limit, we want 3 decimals, is 335, and our upper limit is 0.551. We are good to go. That's it. So we are 99% confident that the true population proportion is between those two numbers, between 0.335 and 0.551. All right, let's try another one. This one asks for a few more items, but we're still just going to use GeoGebra for most of it. So it says, Alice wants to estimate the percentage of people who plan on voting yes for the upcoming school levy. She surveys 380 individuals and finds that 260 plan on voting yes. So my sample size is the 380. My number of successes is 260. We can't do the opposite because our probability, our proportion can't be more than 1. So if we put the bigger number on top, that's not going to work. Okay, so let's let GeoGebra do some work here. We've got, we're going to go to GeoGebra Classic, probability. We're going to click on the statistics tab. We're going to change the drop-down menu to Z estimate of a proportion. We're going to put in the 90%, the 260 successes, and the 380 sample size. At that point, GeoGebra is going to do the work for us. So the first thing it wants is, the sample proportion. So that's p hat. We can do one of two things. We can either divide 260 by 380 in our calculator, or if you come down here to the very bottom, this is actually the sample proportion plus or minus the margin of error. So either way, we want 3 decimals, so that's going to be 0.684, no matter which one you use. But only use the first number. All right, then they want the standard error. So that is right here. Again, they want 3 decimals, so 0.24. Okay, then they want the z-score. So we're going to have to go back up and figure out, we're going to have to see what we need to grab from the table. Well, we know that our confidence level is 90%. So that tells me that alpha is 1 minus 0.90, which gives me 10%. And then I need half of that because we have 2 tails. Okay, so I need z of 5%, right? 0.05. And so that's going to be right there. That's going to be 1.645. So always with confidence intervals, we are going to take 1 minus the confidence level as a decimal, and then divide that by 2, because we need to put whatever's left has to be in both tails. All right, and then finally, after all of that, we have the actual confidence interval. It wants 3 decimals, so we've got 0.645 is our lower limit, and we're going to go all the way up to 0.723. Now on the next page, we're going to interpret that. But you can see GeoGebra does all the work for you except the z-score. We have to read that from the z table. All right, so this is the same problem. They just want us to interpret the answer we got, the confidence interval. So we know we want to be confident. So there's no way we're going to use this one. We want 90% confidence. But then this, we don't want the sample proportion because we already know the sample proportion. We already know P is in the middle. P hat is in the middle of the confidence interval. We want the true population proportion. So we want to be 90% confident that the true population proportion of people who plan on voting yes on the levy is between 0.645 and 0.723. All right, one more of these. Suppose 180 randomly selected people are surveyed to determine whether or not they plan on voting to re-elect the current president. So that's my sample size. Of the 180 surveyed, 36 reported that they will not vote to re-elect the current president. Okay. We want a confidence interval. We want a 99% confidence level. Okay, so we're gonna, just with those 3 items, we're gonna go right into GeoGebra and see what we can find. So we're gonna go to the same place we've been going. Just make sure you change that drop-down window. And we're gonna put in the 99%, 36, and the 180. And then let's see over here. So with the estimate for P, we can either in the calculator put 360 over 180, or we can grab this very first number of the interval. because remember that's P plus or minus E. Right, then we need the standard error. So that is right here. Let's see, 3 decimals, so we went around the 29 up to 30. Okay, now Z is going to take a little work. So we have 99%, so alpha is equal to 1 minus 0.99. And so that's really tiny, that's just 1%. But then I have to cut that in half. So I have a tiny, I have 0.5% in each tail. So that tells me I need to use way over here. So this is going to be 2.576 right from the table. So so the confidence level is 99%. That leaves us 1% that we have to share between the two tails. So we take that 1%, cut it in half. But 0.5% is the same as 0.005. And we have to be careful because we have 0.05 and then we have 0.005. All right, and then finally, we have our confidence interval. And so that will be 0.123 all the way up to 0.277. Yep. So a lot going on, but GeoGebra helps us with all of it except for the z-score, and that we grab right from the table. Okay, so let's go ahead and interpret this answer. Right, this is all the same data from the page before, but we're interpreting. So when we estimate, we want to be confident. So we know the last one's not going to work because we don't see anything about confident. So we want to be 99% confident that the true population proportion of people who will not vote to re-elect the current president is between 0.123 and 0.277.